Thanks for the introduction. So let me start with a brief outline of my presentation. So I'm actually going to give a pretty broad overview of how we exploit parallelism in Gurobi. So I'm going to talk about parallelism in LP and MIP, just a standard multi-core machine. Talk a bit about distributed algorithms, so using multiple machines to solve one problem. I'll talk about distributed MIP, distributed tuning, and distributed concurrent. I'll actually take a look at other metrics, other ways of evaluating parallel performance, and particularly look at maximizing throughput on a parallel server, making the best use of a shared server. And then I'll say a few things about other architectures, so potential for GPUs or quantum computers to help in performance for LP and MIP. So before I dive into the algorithms, I just want to talk about a few important concepts when it comes to parallel computing. The first is sources of parallelism. So basically, where do we find opportunities to exploit parallelism? And in the code, we actually exploit three different sources. So the first is sort of the traditional parallel computing approach, which is you have a fixed pile of work. You have a certain set of computations that you need to do. And you have a set of cores, a set of machines, and you just divide the work up among the machines and things run faster. So we definitely exploit that. We exploit that to the greatest extent possible, or we put a lot of effort into figuring that out. But there are actually two other sources of parallelism that we exploit. Second source is a diversity of algorithms. So if you have a problem that you need to solve, and you have multiple different algorithms available for solving that problem, you can actually run all those algorithms simultaneously on different cores, different machines, what have you, and then the first one that finishes wins. So as soon as the first one finishes, you're done. So this gives you the opportunity to exploit, algorithms that have different performance characteristics. And the third source is performance variability. So if you have one algorithm for solving a problem, but the performance of that algorithm can vary quite a bit depending on, various factors, including randomness. So you can actually exploit the fact that different runs will have different performance characteristics by doing multiple simultaneous runs with different settings, and then again, stopping when the first one finishes. So these are the three sources of parallelism we exploit. Another important concept that I should touch on before diving into the algorithms is non-determinism. So parallel algorithms in general are often known to exhibit non-deterministic behavior. That is, if you have a parallel algorithm, you apply it to a particular instance of a problem. It's quite common for you to, on the same machine for the same exact problem, to get different results each time. And when I say different, I don't mean, wrong answers. I mean, if the problem has multiple possible solutions, it may be that you run the problem multiple times and each time you get a different solution. And we've actually had quite a bit of experience with non-deterministic algorithms, and we've just concluded that they just cause more trouble than they're worth. And so nearly all of the algorithms in Gurobi are deterministic. And when I say deterministic, what do I mean? So if you take the same problem, you run it on the same machine multiple times, you get the same exact result, the same exact computation path each time. So I should add that there are a few algorithms in Gurobi that exhibit mild non-determinism. And what do I mean by mild? So there's some algorithms in Gurobi where there are a few discrete possible outcomes. So, for example, concurrent algorithms, if you're running three different algorithms and the runtimes for the three different algorithms happen to be nearly identical, so it's possible that, in one case, one of them will finish slightly ahead and you'll report that answer. In the other case, the other will finish slightly ahead, you'll report that answer. But in this case, there's only, if you're running three different algorithms, there's only three possible outcomes. So the non-determinism is quite mild there. And a few of our concurrent algorithms have this mild non-determinism. But in general, we've just decided to avoid non-deterministic algorithms. So anything that's highly non-deterministic, we just don't include it in the product. So when it comes to actually achieving non-determinism, it's actually not so simple to achieve. So the basic principle for avoiding non-determinism is, if you've got multiple threads doing something and the first one that finishes, you're going to use that result. You have to answer the question, which one finished first? And if you want determinism, it means what that means is that the answer of which one finished first has to be the same every single time you run it. And how do you decide which one finished first? Well, wall clock time is the obvious choice, which one actually finished first. But because of subtle variations in speed and maybe one of the cores was interrupted and to do something else briefly, so you can't actually rely on the order being the same every time you run the code. So just using wall clock time doesn't give you determinism. There on most CPUs there are CPU counters. So they're counters that allow you to determine, how many cache misses there were, how many instructions were executed, that sort of thing. And these could, in theory, be used to determine which thread finished first, but there's some issues with these. Most of them don't actually produce the same results every time. A lot of cases, you actually need elevated privileges to access these, and so these actually don't turn out to be a very promising avenue for getting deterministic results. And the third is just to instrument the code, which is what we do. And so every algorithm in Gurobi, when you run it, it basically computes a result, and it also computes some estimate of how much work was required to produce that result. And so when you're faced with the question of which thread finished first, each thread, when it's done, says, well, here's the result. Here's the result of the computation, and here's my estimate of how much work was required. And then you just take the result that had the smallest amount of work. You just assume that was the one that finished first. All right, so enough with preliminaries. Now I'm going to talk about parallelism in linear programming. So as you probably know, there are two fundamental algorithms for linear programming. There's the simplex algorithm in its primal and dual forms, and then there's the interior point or barrier algorithm. So I'll come back to this point later, but just a bit of foreshadowing here. So when it comes to considering parallelism, it turns out that there's really more like one algorithm that's important. So simplex is the workhorse. And then barrier, for the purposes of parallelism, it's really more like a very sophisticated procedure for computing an initial basis for simplex. So I will come back to that point. So I'll just leave that there for now. So I'm actually now going to talk a bit about simplex. So the simplex algorithm, so this is a 2D representation of a polytope of a feasible region. Each of the edges represents a constraint, and the blue region represents the feasible region. And simplex traverses the exterior of the polytope. So you are always at a particular point on the exterior of the polytope, at a vertex of the polytope. There's a set of edges leaving that vertex. You pick an edge that improves the objective. In this case, the objective points downward. You traverse that edge until you reach another polytope, and then you continue. And you iterate until you reach a point where there is no improving direction, and because of convexity, that is an optimal vertex. That's an optimal solution to the LP. So that's a graphical representation in terms of the mathematics. So in linear programming, you have a set of feasibility conditions, AX equals B. And what the simplex algorithm does is it partitions the variables into a basis, a set of basic variables, and a set of non-basic variables. So A equals B and N. And then so this is depicted in the figure to the right here. And then your feasibility conditions, AX equals B, becomes B times XB plus N times XN equals B. And the non-basic variables are fixed at set at their bounds. So in order to compute the values of your basic variables, you have to solve the linear system XB equals B inverse times B minus N times XN. And of course, you don't actually compute the inverse of B. You maintain a LU factorization. And then the computation is a sequence of pivots. And a pivot, you basically take a non-basic variable, you move it into the basis, and then you take a basic variable, you move it out of the basis. So it's a series of swaps of one non-basic variable for a basic variable, and each of these steps requires you to update the basis matrix, update the basis factor. There's a variety of housekeeping steps that are required. And if you look at the log from the simplex algorithm, what you see is, so you've got this is a Gurobi log, so you've got the current objective for the current vertex, for the current solution. You've got the primal infeasibility and the dual infeasibility, and when both primal and dual infeasibility are 0, then you found an optimal solution. And the number of iterations in simplex is typically measured in the tens of thousands or potentially hundreds of thousands or millions. So lots of very cheap iterations. In the case of an interior point method, the basic high-level notions are similar. You have a current iterate, you find an improving direction, you iterate until you reach convergence. But in the case of interior point methods, you're not exploring the exterior of the space, you're exploring the interior. And so you take a series of steps, a series of iterates along something called a central path. And eventually you will converge to, so not an optimal vertex, but the center of the optimal face. So nearly every linear programming problem has not just one optimal solution, but a space of optimal solutions. And interior point methods will actually produce a solution that's in the center of the space of optimal solutions. And the actual details here, the basic algorithm, so there's a set of conditions for optimality of an LP called the KKT conditions, the Karush-Kuhn-Tucker conditions. So in order for a solution to be optimal, you need primal feasibility, AX equals B, dual feasibility, A transpose Y plus C equals C, and you need complementarity, complementary slackness, X transpose Z equals 0. And a barrier algorithm, what it does is it basically tries to solve that set of equations. But what it does is it actually replaces the complementarity condition, X transpose Z equals 0, to X times Z equals mu, where mu is a centering term. And you start with a certain mu. At each iteration, you decrease mu, and when mu gets small enough, you are close enough to the optimal solution. From a computational point of view, from a linear algebra point of view, what you do is you take this system of nonlinear equations, you linearize it, essentially Newton's method. You do a bit of linear algebra, you wind up with the following. So you need, at each iteration, you need to solve a linear system. A theta inverse A transpose dy equals B. So A is your original constraint matrix, B is your original right-hand side, and dy is the direction vector in the dual variables, the step in the dual variables. And then you iterate, you reduce mu in each iteration, and it's a provably convergent algorithm. So you do this for enough steps, and you wind up at in the center of the optimal face. If you list the steps involved in an interior point solver, there are actually quite a few. There's some setup steps, some things you do up front. So you do a pre-solve to reduce the size of the original problem. You do a fill reducing ordering to reduce the cost of the factorization, and symbolic factorization to compute the structure of the factorization. And then in each iteration, you do some linear algebra. You form this A theta inverse A transpose matrix. You factor that matrix, you do a solve, you do a few other computations. The dominant computation here is the factorization. It's a Cholesky factorization of A theta inverse A transpose. And then once you're done, so you, in theory, once the iterates conclude, you have a solution that's in the center of the optimal face. You could just use that solution, but in almost all cases, what you want to do is a crossover to a basic solution. And this is especially true in MIP, where the MIP algorithm really depends on having bases in order to work quickly. So if you look at the log, if you look at a log from the barrier solver, so I'm not going to go through this in detail, but the key point to note here is that we're doing a small number of iterations, 13 in this case. In each iteration, we have a primal iterate and a dual iterate, which has a certain primal infeasibility and dual infeasibility and complementarity. And when all of these reach epsilon, it gets small enough, then you declare the solution to have converged, and that's your optimal solution. And then the crossover step, basically once you have that interior solution, you apply a crossover algorithm. The crossover algorithm does a few iterations, and when you're all done, you have a basic solution. So key essential differences between simplex and barrier. So simplex does thousands or potentially millions of iterations on extremely sparse matrices. And so the iterations in simplex are incredibly cheap and just aren't doing that much work. And so one result of that is that there's actually not that much opportunity to exploit parallelism. I mean, there's some opportunity. Some people have written parallel simplex codes. Generally the performance improvements are small and sometimes zero. Sometimes it's unusual to see more than a few percent performance improvement for parallel simplex. In the case of barrier, so we're doing dozens of iterations, but these are expensive iterations. And the reason they're expensive is the matrices are much denser. It's much more expensive to factor A theta inverse A transpose than it is to factor B. And so there are actually lots of opportunities to exploit parallelism. Parallel Cholesky factorization is a well-studied problem, and it's known that you can get a lot of parallelism. So there's a but here. I'll come back to the but in a second. First, I want to talk about concurrent LP. So as I mentioned earlier, one opportunity for exploiting parallelism is if you have multiple algorithms for solving the same problem, you just run them simultaneously on different cores, different machines, whichever one finishes first wins. So our default LP solver is actually concurrent LP. And if you've got multiple threads, multiple cores, so if you've got one core, we use dual simplex. If you've got two cores, we use dual simplex on one core and barrier on the other core. Three or four cores, we use the next cores for parallel barrier. Thread 5, core 5, we use for primal simplex. And if you've got 6 or more cores, we apply the rest of the cores to barrier. And I mean, it gives you a nice mix of speed and robustness. So if for a particular type of problem, one of the algorithms works particularly well, so this will just automatically notice that and give you the benefit of that. And we have deterministic and non-deterministic versions of concurrent LP available. So let me say a few words about performance of these various options. So what I'm showing here is performance results for two different machines. On the left, the table is for a 4-core Intel Xeon machine, on the right, a 16-core AMD EPYC machine. And I've taken a test set of problems, about 1,300 linear programming problems. And then I've run primal simplex, dual simplex, barrier, deterministic concurrent, and non-deterministic concurrent on those machines. And note that if we're running a simplex algorithm, or we'll just use one of the cores in the machine. If we're just running barrier, we'll use all the cores for barrier. Otherwise, the cores are applied as indicated on the previous slide. And we're just looking at models that take more than 1 second from our test set. And what's reported in the table is geometric means of performance, geometric means of ratios of runtimes. And we've just chosen concurrent, which is our default, to be 1.0. So that's, we've just chosen an arbitrary baseline. And what you can see, so one question you're going to ask is, what's the cost of determinism? What's the cost of requiring that we get the same exact basis every time? And on 4 cores, the cost is on average about 13%, 1.13. 16 cores, the cost is 20%, 1.20. And then when it comes to the individual algorithms, what you see is the concurrent approach is actually the fastest overall. So that's the 1.0. There's no value less than 1.0 in the table. And then deterministic concurrent is slightly slower. If you just use barrier alone, that's slower than concurrent, but it's not that much slower. 20% on 4 cores, 27% on 16 cores. And then dual simplex is roughly a factor of 2 slower than barrier, and primal is roughly a factor of 3 slower than barrier on average. You know, as I mentioned, so different problems can get different results. So primal simplex and dual simplex, they do beat barrier on a lot of models, but on average across the whole set, barrier is the fastest individual algorithm. All right, so as I mentioned, barrier can exploit parallelism. Simplex, it's much harder. So given that, it's maybe surprising that on 16 cores, barrier is only about a factor 2 faster than dual simplex. So what I show in this slide here is the speed up from adding more cores to barrier. So I've taken the same LP test set, around 1,300 models, run on an AMD EPYC 7282 machine, a 16-core machine. And I look at performance for a multi-core run versus performance on a single core. And I actually split this out by the time required to solve the model. So the first line shows performance results across all models that take at least 1 second to solve. Second line, models that take at least 10 seconds to solve, and third line models that take at least 100 seconds to solve. So you can think of this as, you know, the models that take more than 100 seconds are the harder models. And what you see is as you add cores, as you go from 1 core to 2 cores to 4 to 8 to 16, performance improves. But it tops out at a level that is well below the number of cores in the machine, well below 16 cores. So on average across the whole set, the models that take more than 100 seconds, parallel barrier gets a 2.5x speed up compared to barrier running on a single core. And given what I said about how Cholesky factorization can be parallelized nicely, you know, it's a pretty obvious question, why are we only getting 2.5x speed up on 16 cores? So one thing I've done here is I've broken down runtime into the different components of barrier runtime. And I'm actually only showing the 4 most important components. So pre-solve, every model we apply a pre-solve, that's sequential. The Cholesky factorization, the triangular solves, and the crossover. So those are the 4 components here. And you know, conventional wisdom is that the factorization is the dominant cost of solving a LP problem using barrier. And indeed, on 1 core, what you see is barrier is somewhere between 40 and 45% of total runtime on average. This is for models that take at least a second to solve. But the factorization parallelizes nicely. So as you add cores, the cost of that factorization drops. And this is something called Amdahl's law. Basically, as you add more cores, the things that run nicely in parallel drop off, and the things that don't become dominant. And so on 16 cores, what you see is actually the dominant cost is the crossover. And I didn't say much about the crossover algorithm before. So what is the crossover algorithm? Well, I mean, to a first approximation, it's basically simplex. So you have a basis, you're pivoting columns in, you're pivoting columns out. Computationally, it looks just like simplex. And indeed, it has very limited opportunities for parallelism. So, you know, on 16 cores, the dominant cost of barrier is actually crossover, simplex. So 30% on average of the runtime goes to simplex. And you may look at this and say, well, yeah, this is for models that take more than a second. But you know, on the bigger models, on the harder models, the picture is going to look different. And indeed, it does look different. So these are results for models that take more than 100 seconds. And indeed, what you see on 1 core is that factorization is in fact a bigger part of total runtime. It's closer to 50% of total runtime. But as you add cores, again, the cost of the factorization drops, the relative cost of the crossover increases. And in fact, for the harder models, crossover is an even more dominant fraction of overall runtime. 45% of overall runtime on average goes to crossover. So there are some constraints on parallelism for LP. So now let me talk about MIP. So just so we're all on the same page, this is a branch and bound tree. So MIP is LP-based branch and bound. So it's all about solving relaxations, branching, creating subproblems. exploring a tree of possible solutions. So you solve your root relaxation, you relax the integrality constraints, you solve an LP. Some of the variables that are supposed to take integer values don't in the relaxation, so you pick one. Let's say v is equal 3.5 in the relaxation. It's an integer variable, so you know that it's either less than or equal 3 or greater than or equal 4. That creates two subproblems. So you've taken your original problem, solved the relaxation, cut off that relaxation solution, and created two subproblems as a result. You continue that process. At a certain point, your relaxation may take an integer value, may take integer values, and so that is a feasible solution to your MIP. You can compare that to the best solution you've found so far. If it's the best, you have a new best solution. You have a new upper bound. You continue exploring. Some relaxations may be infeasible. So you solve the LP relaxation. There is no feasible solution, which means there can't possibly be an integer feasible solution in that subtree, in that subproblem. So you can prune that. You continue. At each point, you have a upper bound, which is the best solution you've found so far. And you have a lower bound, which is essentially the worst bound on the value of the objective value for a solution among all the unexplored nodes in the tree. And those get closer and closer as you explore, and eventually they become equal, and then you found the provably optimal solution. All right, so when it comes to parallelism, so MIP explores a tree of relaxations. The frontier nodes, the nodes that have not yet been explored, they're independent, and so they can be explored in parallel. And so, at some level, it's an obvious and potentially embarrassing source of parallelism. But reality is quite a bit. So here are parallel speedups as we add cores. This is our internal MIP test set, so around 4,000 models, again on a 16-core AMD machine, and these are speedups relative to one core. So one core is 1.0, and again we have numbers for models that take at least 1 second, at least 10, at least 100, and at least 1,000. So models that take at least 1,000, these are the harder models, and greater than 1, this is the majority of the models in the set. And what you see, for example, on 16 cores for the harder models, a factor of 4.22 average performance improvement across the whole set. So these are geometric means of ratios of runtimes for one core versus 16 cores. So 4.22 average across the whole set of models that take more than 1,000 seconds. It's nice to get a factor of 4, but this is you're using 16 cores, so it'd be even nicer to get 16-fold improvement. So what is limiting the parallelism? Was limiting the ability to exploit multiple cores. Actually, I'm going to skip that slide. So there's really one thing that limits parallelism, and that's the shape of the search tree. And there are a few different aspects to the shape. So there's the fraction of time spent at root, the total number of nodes explored, load balancing, and the topology of the search tree. I'll actually talk about each of these. First, I want to talk about the fraction of time spent at the root of the branch and bound tree. So, if you draw a figure, if you draw a figure of a branch and bound tree, basically, it's natural to make each node the same. And so it's natural to assume that the amount of work associated with each node is comparable. But the reality is that the root node is a special node. It's a particularly expensive node. And it's also, important to note that when you're at the root, there are no other nodes. And so when it comes to parallelism, it's not like the other threads can go off and do something else. There's one root node, and basically there's one thread that's going to be working on that root node. So why is that node so expensive? Well, let me talk a bit about what happens at the nodes of a branch and bound tree. So if you look at each node, if you look at the flow of the MIP branch and bound, so the first thing you do is pre-solve. So you take the original problem, you reduce it to a simpler form. Next thing you do is node selection. So if you're at the root, there's only one node, so node selection is easy, but in general, you have to pick a node from your branch and bound tree. And then there's a set of things you do at each node. You do a node pre-solve, you solve the LP relaxation at that node, you generate cutting planes, potentially in a loop there. You apply heuristics to try and find feasible solutions, and then you apply branching to choose a branching variable and create child nodes. So lots of things are happening inside of each node. At the root node, this loop is restructured a little bit. And so at the root node, so we do a node pre-solve, we solve the root LP relaxation, generate cutting planes, perform heuristics, and then we loop back. And so I've noted the steps that are different here in red. So let me say a few words about these. So the root LP relaxation. So this is different from what happens at the nodes, and the main reason is that at the nodes, the difference between the current node and the parent node is that we've added one bound. And we have a basic solution to the parent, and so it's typically cheap to re-optimize. You add a bound, you apply dual simplex, typically you do a few dual simplex iterations, and you have a new optimal solution for your child node. In the case of the root, I mean, we don't have an initial solution, so we're starting from scratch. So we have to solve that problem from scratch. It's just more expensive. And then heuristics and node pre-solve, so I highlighted those because those are now inside the loop. So the root node is potentially going to do multiple passes of heuristics, multiple passes of node pre-solve. How many passes? It depends on the problem, but 10 passes is not unusual. 20 passes is actually fairly common. And so a key point here is that there's a lot of work going on at the root that isn't necessarily happening at each branch and bound node. And an obvious question, if we have lots of cores and if the root node is taking all this time and we can't exploit parallelism at the root, well, why not just do less at the root and push more work into the nodes? And one of the, I guess, dirty little secrets of branch and bound when it comes to MIP is that branching just isn't that effective. And so you'd have to do a lot of branching to make progress to solve a MIP problem. And it's often the case that doing a little bit of work at the root can save you a lot of work in the branch and bound tree. So it just doesn't pay off to do less work at the root. So how do we exploit parallelism at the root? Well, so there's options. So one thing we do at the root is we actually exploit performance variability. So in fact, we don't just solve one root, we solve multiple roots. And each root has some subtle difference from the main thread. So change the random number seed, change a parameter, change something, with the hope that if we have multiple independent roots solving, that if one happens to solve better than the others, produces better results, that we will be able to exploit that. And so we have our main thread, which is performing the steps in the root. We have our helper thread, which is performing the same steps, and then as it generates cutting planes, as it applies heuristics, as it does various things, it feeds the results back into the main thread. And so the main thread integrates the results from the helper. And then when we're done at the root, the helper basically just gets discarded, so that we don't pursue that root, we discard it, and then we pursue the main root, use that as the basis of a tree exploration. So what's the benefit of doing this? There's some benefit. It's pretty small. You can measure it in single-digit percentage, but there's some opportunity to exploit parallelism at the root. But it's a pretty serious bottleneck. So another thing that limits parallelism is the total number of nodes explored. Clearly, if you've got a lot of cores and you're not exploring a lot of nodes, that's going to limit your ability to distribute nodes among cores. So this graph shows the number of models among the models in our test set, the number of models that explore more than 100 nodes, the number that explore more than 1,000, and the number that explore more than 10,000 nodes. And as you can see, the number of models that explore more than 10,000 nodes, it's just over a quarter of the total models in the set. And so it's not typical to explore a huge branch and bound tree. So if you have more nodes, then that does allow you to exploit parallelism better. And so what this graph shows is parallel speedups where you take the number of nodes required to solve the problem into account. And so what we've done on the y-axis, we have the average parallel speedup on 16 cores. And we have 3 different lines. The blue line shows the average speedup for models that take more than 1 second, more than 10 seconds, more than 100 seconds, and more than 1,000 seconds across the full set of problems. These are the numbers from the table I showed earlier. And then the red line shows the average parallel speedup just among the models that take more than 100 nodes to solve. And the green line shows the average speedup among the models that take 10,000 nodes or more to solve. So indeed, if you have more nodes, you're going to get better parallel speedups. We get more than a factor of 5 average on 16 processors among the models that take more than 1,000 seconds and explore more than 10,000 nodes. So there's some, and these are of course averaged across a broad set. On any particular model, you can easily get much higher, much better speedups than this. So another thing that limits parallelism is load balancing. So again, it's tempting when you look at a branch and bound tree to think of every node as the same. But in reality, the cost of solving a node in the branch and bound tree can vary wildly. It's not that unusual for some nodes in the branch and bound tree to take 100 times longer than other nodes. And so, as you're dividing up work, if you're dividing work among, say, 16 processors, and you hand one processor a node that takes 100 times longer than the other processors, than the other nodes, that's potentially going to create load balancing issues. So you're going to leave some of the other processors idle, and that can be a substantial issue. And then finally, the topology of the tree. So when you talk about, how many nodes are required to explore the branch and bound tree, if I say it takes 1,000 nodes, that doesn't tell you the whole story. So it's quite possible that the 1,000 nodes look something like this. We have a root node, you branch left, you keep branching left. After 1,000 nodes, you get to the bottom of the tree, you find a feasible solution, and in fact, it is a provable optimal solution, so you're done. Of course, if this is the situation, then if you have 1 core, 2 cores, 4 cores, it doesn't matter. Basically, it's just a race to a leaf, and adding more cores is not going to speed that up a lot. And so there are actually a fair number of models where the topology looks more like this than it does a full bushy tree. So there are clearly things that limit parallelism in MIP. So as I said, the average improvements are still substantial. And as you explore more nodes, as the problems get harder, the scope for improvement from parallelism improves. But there are definitely constraints on how much parallelism is available. So now I'm going to talk about other options for exploiting multiple cores. First one I want to talk about is concurrent MIP. So the options I've talked about so far in MIP, basically you've got multiple cores that are all exploring the same tree. With concurrent MIP, you can have multiple cores exploring different trees, so totally different independent jobs. And it's actually pretty simple to exploit this. We've got a parameter, concurrent MIP. You just set this to the number of jobs you want to run simultaneously. And we will automatically divide up the available cores. So if you set the parameter, for example, to 4 on a 24 core machine, then you will get 4 jobs, each of which uses 6 threads. And then basically we combine the results automatically. So it looks like there's a single run from the point of view of the log, but in fact, it's multiple independent runs with the results being combined automatically. This is non-deterministic, so mildly non-deterministic. So we don't guarantee that you'll get exactly the same result every time. So why does this, when is this useful? Well, this is a way to exploit performance variability. So, if you've got a model where performance can vary wildly, having multiple, perhaps random runs can reduce your runtime. Another thing you can do here is you can focus on different goals simultaneously. So, for example, you could have 2 independent jobs where one is focusing exclusively on moving the lower bound. So it's being, aggressive, generating cutting planes. It's doing the things that move the lower bound. And the other thread could work just on the upper bound, so heuristics, that sort of thing. So in general, concurrent MIP is actually, it's not as effective as you might hope. So you get some performance benefit, but in general, having all your cores applied to the same problem is more effective. But there are some important exceptions. So there are some cases where concurrent approaches actually win. So I've got a log file here. It's actually very simple to use concurrent MIP. So we've got a setting called Concurrent Settings, which allows you to just create a set of parameter files. So you create multiple files where each one sets a set of parameters, and you just list those files in the Concurrent Settings parameter. So here are log files for a difficult model DG012142. On the right here, this is the log for using default settings. So basically this shows after 30 seconds, I stopped the run after 30 seconds. So this column here shows your best incumbent, your best objective value, 3.6 times 10 to the 6th, and your best lower bound, 7.8 times 10 to the 5, with an optimality gap of about 78%. And on the left here, what I've done is I've used the concurrent settings parameter, and I've input two different parameter files, MIPFocus1 and MIPFocus3. Each of these files just contains a single line which sets the MIPFocus parameter to 1 in one case and 3 in the other. So MIPFocus1 asks the solver to focus on finding feasible solutions, MIPFocus3 to focus on improving the lower bound. And what you can see in this case, so we get our best incumbent after 36 seconds, roughly the same amount of time, is 2.7 times 10 to the 6. Our lower bound is 8.6 times 10 to the 5. So 68% gap as opposed to 78%. So in this particular case, this concurrent approach gives a better result. Now I'm going to say a few words about distributed algorithms. So everything I've talked about so far, you use one multi-core machine to solve your problem. But we actually have algorithms that allow you to apply multiple machines, multiple boxes connected on a network. And so it's a manager-worker paradigm. So you have one manager that distributes work among multiple workers. The workers perform the work, they report the results back to the manager, and the manager collects the results and doles out more work. So one option we have is distributed MIP. This is basically just the distributed version of our parallel MIP. So we have one branch and bound tree. We explore it on multiple machines, each machine with multiple cores. So you can apply lots and lots of cores. And I say it's a distributed algorithm. It's actually a combination of a concurrent and a distributed algorithm, and a parallel tree exploration. So we start out by doing essentially a concurrent solve. So each machine gets a copy of the model, goes and solves independently, different parameter settings on different machines. And then at a certain point, after a certain amount of time, we just stop all the nodes and basically ask which of you had made the most progress. And then we essentially kill all the other runs, and we take the machine that made the most progress, and then we apply all the machines to continuing to explore the branch and bound tree from that best node. And one thing this gives you is dramatically higher node throughput. So you can blow through nodes with a distributed MIP solver extremely quickly. And as I've talked about, there are limits to parallelism in MIP, but if you've got a model which makes lots of nodes available, a distributed MIP solver is just going to blow through them very quickly. So here's some measured results from a model from MIPLib, DanoInt. On one machine, this is a 4-core machine. I used Intel Xeon E3s, 4-core machines. One machine, about 2,000 seconds, just under 2,000 seconds to solve it, about just under 1 million nodes. On 16 machines, roughly a factor 10 faster. And then on 32 machines, roughly a factor of 15 faster. So some pretty substantial improvements are possible. And it's problem dependent, but we have some customers that are consistently across a broad set of their problems seeing 10x performance improvements. And where do you get 16 or 32 machines that are identical? Well, simple answer is you can get them on the cloud. So it's trivial using our instant cloud to go and request 16, 32, 64, whatever identical machines. And then we also have a distributed tuning option. So we have an automated parameter tuning tool. It'll try and find the best parameters for your problem. It's very compute intensive, but we have a distributed version. You just say tune jobs equals n, and then it'll just go and use multiple machines to try different parameter settings. It's trivially parallel. So, with 24 machines, something that would take a day takes an hour. And it's quite effective. So inside the company, in our support team, we actually do a fair amount of customer parameter tuning. And I'd say pretty much all of that is done using our distributed tuning tool. All right, so next thing I want to talk about is other metrics, basically other ways of evaluating parallel performance. And specifically what I want to talk about is, let's say you have a multi-core machine and it's a shared machine. So you've got multiple users all sharing that one server. So the question is, if you have a job that you want to submit to this machine, how many cores should you request? And of course, if you request too few, if you're too polite and say, oh no, I don't want to use all the cores in the machine, then you potentially leave cores idle if nobody else is running. And so that's a waste of resources. Your job will probably take longer than it needs to. But if you ask for too many cores, you ask for every core in the machine, and a bunch of other people simultaneously ask for every core in the machine, then you've got multiple jobs fighting over cores, and that could potentially have a negative effect on performance. So here are results of a simple test. So what this table shows is, normally we talk about the time to complete a job. But in this case, time to complete the job is actually, it's one metric, it's a relevant metric, but it's not necessarily the most important metric. The most important metric is, if you've got a server, you've got a bunch of jobs, how many jobs can you pump through that server per hour? And so what we've done here is we've taken a model, dano-int, and we've varied the number of threads that were requested for one instance, for one job. So we're basically saying, I'm going to take this model dano-int, and I want to solve it on using 12 threads, using 24 threads, and then using 19 threads. I'll explain why 19 in a second. And then I'm going to look at throughput for this one server. It's a 24-core server. If I submit one job simultaneously, 2 jobs, 4 jobs, 8 jobs, and 16 jobs. And so what you see is, if I run a single job, and I ask for 12 threads, so the machine has 24 and I'm only asking for 12, then that machine is going to solve 15 models per hour. So it's going to pump through 15 jobs per hour. And then if I double the number of jobs, so now I've got 2 jobs, each asking for 12 cores, well, my throughput almost doubles. So there's some contention for resources, but I've got 2 12-core jobs running on a 24-core machine. This seems like they would coexist quite nicely. So now I'm starting to oversubscribe the machine. I'm starting to ask for more threads more cores than are actually available in the machine. But if I actually ask for 4 jobs, 12 threads each, so 48 threads total, my throughput actually continues to increase from 28 to 39. And then the interesting thing is, as I continue oversubscribing the machine, so 4 jobs to 8, 8 jobs to 16, performance starts to drop off a little, but just a little. And so in this case, I've got 16 jobs, each asking for 12 threads. So I'm asking for 192 threads total on a 24-core machine, and throughput is still good. And then, similar sorts of numbers, if I ask for 24 threads per job, so one job, I get higher throughput than I would asking for 12 cores. And then throughput increases, and then once I start oversubscribing the machine, the throughput starts to drop off, but not that much. And then these 12 and 24, these are nice multiples of the 24 of the number of cores in the machine. So you may reasonably ask, well, what happens if I don't carefully arrange it so that the number of threads is a nice multiple of the number of cores? So here I ran 19 threads, 8 jobs and 16 jobs, and you see you get pretty similar results. And so the bottom line is if you've got a shared resource and you're worried about how to allocate threads to jobs in order to avoid contention, you don't really need to worry. So basically the things work out, the machine can deal with it. So, so last part of my talk, a few more slides. So people often ask us about using GPUs for solving MIPs. So this is a nice figure from NVIDIA. Basically, it shows the difference between a CPU and a GPU. CPUs devote lots of the chip to control logic, caches, etc., and not that much to cores. GPU, on the other hand, most of it's devoted to cores, very little devoted to caches and control logic. The key point I want to make here is, this control logic is what allows the different cores to do different things. And in fact, on a GPU, you've got dozens or potentially hundreds of cores that have to do exactly the same thing, or almost exactly the same thing. It's called a single instruction multiple data model. And if you look at the work involved in solving a MIP, basically exploring a branch and bound tree, indeed, you've got lots of nodes. The nodes may look similar at a high level, but the reality is that each node is very different. It's got a different basis. You've changed a different bound. The work involved in each one is quite different. And so it's just not easy to exploit a model where you have to apply hundreds or even thousands of cores all doing the exact same thing in each step to a problem where there's some diversity in the different nodes. So there's some opportunities to exploit a GPU. In particular, the factorization and barrier can exploit a GPU. But as we discussed, the factorization is actually not the computational bottleneck for barrier in most cases. And then finally, quantum computing. So there's a lot of excitement about quantum computing. And in fact, there's a company, D-Wave, that makes a quantum computer. And if you go to their website, the first application they list for their computer is optimization. And it's early in quantum computing. So it's an interesting future technology. There's clearly the potential for this to do interesting things, but currently it's still a science project. And I've had conversations with many people who are excited about quantum computing and using it for optimization. And it's quite common for them to basically say, well, optimization problems, wouldn't it be nice if you could solve these? And we need to wait for quantum computers to solve these. And in a lot of cases, they're just not aware that optimization is a field with a long history and lots of quite effective codes for solving a variety of problems. So quantum computing, it's interesting for the future, but the future seems to still be a ways off. So quickly, conclusions. So we use parallelism throughout the Gurobi optimizer. Basically, if there's an algorithm in the code and there's an opportunity to exploit parallelism, we've probably tried to exploit it to the extent possible. So LP, MIP, distributed tuning. Performance improvements are significant, and in most cases, you don't actually have to do anything. We just automatically grab the available cores and use them. They're far from linear though. So on a 16-core machine, you shouldn't expect to get 16-fold parallelism, although they are problem dependent. So there's some models where you'll get substantial improvements from multiple cores, and there's some where you won't. And parallelism is something that continues to grow, so it's a continued focus area for us. So we continue to try and push parallelism forward.